In 1985, the devastating Mexico City earthquake brought down thousands of buildings. Amidst the rubble, a terrifying phenomenon was clearly documented. Structures collapsing, not due to internal failure, but because of physical collision with their neighbors. This is a real-world example of structural pounding. The moment two buildings, instead of swaying independently, absorbed each other's destructive forces. This catastrophe was the result of one simple omission: an inadequate seismic separation gap, or building separation joint. Structural engineers have a vital, calculated solution to prevent this deadly scenario, a necessary space often overlooked on blueprints. Today, we're going to uncover how a small strategic gap can protect hundreds of tons of steel and concrete from total destruction during a quake. I'm your host at Constructive Minds, and in this few minutes of instruction, you'll not only understand the mechanism of structural pounding, but you will also learn the exact prescriptive formula for calculating the minimum safe distance, complete with a full numerical example that justifies a 30-centimeter separation. If you are serious about preventing design failure, stay with us until the very end.
You know that thin, dark line you sometimes see between two massive skyscrapers? Well, it's not a design flaw, and it's definitely not wasted space. Turns out, in a major earthquake, it's pretty much the only thing stopping those two buildings from destroying each other. This is the story of a calculated void, an invisible shield that's one of the most important and overlooked safety features in our modern cities. See, we tend to think of an earthquake as this epic battle between one building and the ground shaking underneath it. But the real danger, the one that engineers learned about the hard way, is often the building right next door. A skyscraper can be perfectly designed to survive the shaking, only to get hammered into a catastrophic collapse by its neighbor. And to really get why this happens, we have to go back in time, back to a moment that completely changed structural engineering forever: Mexico City, 1985. It was right here that a devastating earthquake revealed this deadly phenomenon that until then had been tragically underestimated. So on September 19th, 1985, a massive 8.0 magnitude earthquake just rips through the city. For minutes that must have felt like an absolute eternity, the entire skyline just danced violently. And in the aftermath, as rescuers were digging through the rubble, engineers started to notice this horrifying pattern. It wasn't just that buildings had failed on their own. Thousands of them had collapsed because they had literally battered each other to death, over and over again with unimaginable force. This terrifying result actually has a name. It's called structural pounding. It's what happens when two buildings right next to each other, each moving to its own deadly rhythm during a quake, smash into one another. And we're not talking about gentle taps here. These are massive, brutal impacts that create forces the buildings were never, ever designed to handle, leading to serious damage and, way too often, a total collapse. So why does this pounding even happen? I mean, why don't buildings that are right next to each other just sway together in sync with the ground? Well, the answer lies in the fundamental physics of how different structures respond to all that seismic energy. They basically become these chaotic, uncoordinated dance partners in a disaster. First off, let's cover a basic principle. When an earthquake hits, modern buildings are actually designed to be flexible. They sway back and forth, and that helps dissipate the quake's immense energy. Engineers call this side-to-side movement lateral displacement, and it's actually an intended natural response for a building. And this is where the problem really becomes clear. A tall, flexible skyscraper, it moves slowly with this long, kind of lazy sway, almost like the end of a whip. But its neighbor, say a shorter, stiffer building, reacts completely differently. It shakes back and forth really fast with a quick, jerky motion. So just try to imagine these two very different dances happening inches apart. A collision becomes almost inevitable, right? The key thing here is that every single object, from a guitar string all the way up to a skyscraper, has what's called a natural frequency. You can think of it like a person's natural walking pace. It's just the unique rhythm that an object wants to vibrate at. And because no two buildings are identical in their height, their mass, and their stiffness, their natural frequencies are different. And it's that fundamental difference that causes them to sway out of sync and, well, smash into one another. Okay, so if we know buildings are gonna sway, and we know they'll sway differently, how in the world do we stop them from colliding? This is where the engineering provides a really elegant solution. It's not guesswork, it's a precise formula that's used to create a life-saving safety zone. The process is actually pretty straightforward. First, engineers figure out the absolute maximum distance the top of Building 1 is expected to sway in a big earthquake. Then, they do the exact same math for Building 2. Finally, they just combine those two numbers to figure out the minimum gap they need to leave between them. Let's walk through a quick example. All right, so our first building is a modern 12-story structure designed to be pretty flexible. A preliminary analysis shows that during a design-level earthquake, its roof is probably going to move about 50 millimeters. But that's just the starting point. You see, that initial 50 millimeters is just the elastic movement. That's the sway the building can handle without any damage. To account for the much larger real-world sway during a major quake, engineers apply something called a deflection amplification factor. For this building, that factor is 5.5. So we multiply 50 by 5.5, and we get the real number we need to worry about, 275 millimeters. That's how far it could truly move. Now let's look at its neighbor. This one's an older, shorter, and much stiffer 4-story building. And just like you'd expect, its initial calculated movement is a lot smaller, only 20 millimeters at its roof. This one shakes more than it sways. So again, we apply a safety factor. Because this building is stiffer and less ductile, its amplification factor is a bit lower, at 4.5. We multiply 20 by 4.5, and that gives us its total expected movement, 90 millimeters. So you have one building swaying 275 millimeters while its neighbor is moving 90. So how do we combine these two numbers? I mean, we could just add them together, but that's actually too conservative, because it's really unlikely both buildings will hit their absolute peak sway in opposite directions at the exact same instant. Instead, engineers use a smarter, more statistically sound method called the square root of the sum of the squares, or SRSS. I know it looks a little complex, but it's really just a clever way of combining the two potential movements. So we plug in our numbers, the square root of 275 squared plus 90 squared, and the math gives us our magic number, 289.3 millimeters. That's almost 29 centimeters, or about 11.5 inches. That is the absolute minimum safe distance needed to prevent a catastrophic collision. A gap just under a foot wide is literally all that stands between safety and disaster. It's incredible. But, creating this safety zone is a lot more complex than just telling the builders to stop 29 centimeters short of the property line. The gap itself has to be meticulously designed and detailed to make sure it works correctly, not just during an earthquake, but every single day. And it's really important to know the difference between the gap we're talking about, a seismic joint, and something that looks kind of similar, called a thermal joint. A thermal joint is just for small, slow movements caused by materials expanding and contracting with temperature changes. A seismic joint, on the other hand, is designed for one thing and one thing only, handling the massive, rapid, and unpredictable movements of an earthquake. They are absolutely not interchangeable. Now, for a seismic joint to work, the separation has to be absolute. You're essentially creating two totally independent structures standing side by side. The gap can't just be in the walls. No, it has to run from the very top of the roof, down through every single floor slab, all the way down to, and sometimes even through, the foundations. Even things like utility lines need flexible connectors. Any single rigid thing bridging this gap becomes an instant point of failure. But of course, you can't just leave a 29-centimeter open trench running through your building, right? So the gap is bridged with these specialized flexible joint covers. They let people walk or drive over it, but they can slide open and closed during a quake. And crucially, special accordion-like fire barriers are installed inside the gap. These things compress and expand with the building, and they stop fire and smoke from racing between floors or even between buildings. So the next time you're walking through a city and you see that thin line between two buildings, I bet you'll see it differently. It's not some oversight or wasted real estate. It's a deliberate, highly calculated, and totally invisible shield. This gap is not wasted space. It is space reserved for survival. It's this quiet testament to the hard lessons we've learned from past tragedies, and it's a constant guardian standing between our cities and catastrophe. I mean, it's engineering at its finest, a really simple concept that solves an incredibly powerful and complex problem. It really makes you wonder, doesn't it? Our world is just filled with these kinds of ingenious solutions, hiding in plain sight. What other invisible engineering, what other hidden gaps or clever designs are out there working silently to protect you every single day? It's a question worth thinking about.
The seismic separation joint is a sophisticated structural solution. It transforms a potential catastrophe, the destructive force of building pounding, into a manageable, calculated space. It reminds us that often, the difference between failure and survival in a major seismic event lies in the details we cannot see. This gap is not wasted space. It is space reserved for survival. Thank you for joining Constructive Minds for this technical deep dive. If you found this valuable, hit that like button and subscribe for more specialized civil and structural engineering content. Click the bell icon so you don't miss our next video, where we break down the secrets of base isolation technology. Build smart,